Okay, to wrap up this module, I now want to finish up the optimization study of this supply chain network and talk about a simulation analysis of one of those single consolidation points that we were looking at in the strategic optimization model. So here, if you recall from previous lectures, we were looking at this large intermodal supply chain where we had suppliers, consolidation points, and distribution centers, and we were strategically determining which suppliers would ship their goods through which consolidation points, and therefore which consolidation points would then take those goods and send them to which distribution centers. In this portion, we're actually looking at a single box, a single consolidation point, and the dynamics or the actual operations within this consolidation point. Now, what are we modeling here? Well, we're going to build a simulation model of a generic consolidation point. Generic from the standpoint of we can change the data and the assumptions of that consolidation point to make it represent any consolidation point that we choose. The following aspects that we're going to be covering are, first of all, the inbound freight process. So this less than truckload freight that shows up to the consolidation point, we have to figure out which dock door that inbound truck is going to be assigned to. What purchase orders are actually on that truck coming in. So now we're at a much lower operational level than the high-level strategic operational model. We're actually going to be simulating real purchase orders that come in from suppliers and where their destinations are intended. In addition to the inbound process, we have to simulate the outbound process, because if goods flow into the consolidation point, we have to make sure we know how to build the outbound trucks. So the idea of outbound trucks, which dock doors they need to go to, as well as how we can flexibly dispatch different cross-dock purchase orders to outbound trucks. What we're talking about here is the idea of if there's an inbound truck being unloaded and it has goods on it destined for a truck that is already assigned to an outbound dock door, the process of cross-docking is that we want to take it directly from the inbound truck to the outbound truck. We don't wish to store it in inventory, to store it for any additional cycle time or have any additional excess handling. Well, if we're going to move stuff from inbound doors to outbound doors, we also have to model actual resource contention for the dock doors. We need to model the dock doors and know who or what is occupying them. People required to load and unload, making sure the material handling equipment, the forklifts are modeled. Because at the operational level, we can't just assume that a truck comes in and a truck goes out. We have to have the people and the equipment and the resources to actually perform the loading or the unloading. We also have detailed purchase order modeling, because we have to know not just a truck comes in, but what specifically are we assuming is on that truck? What's representative for what could be on an inbound truck? What is representative for the destinations in terms of the distribution centers that this consolidation point would be shipping those purchase orders to? So we need to generate both an origin and a destination for each purchase order, as well as the size of that purchase order with regard to both weight and to its cube or volume, because as we talked about in the optimization model, we have weight and cube limits on our vehicles. Well, now we're actually going to generate that from historical data to get a representative sample of actual goods flowing into our consolidation point. So why would you do this simulation? Well, we could do a tactical analysis based on our optimization study, such that we can look at, the optimization model recommended these new routings of suppliers to consolidation points to distribution centers. Well, we want to see how that's going to impact consolidation point performance. Can it handle the demand? How can it handle the demand over time as we see this 5-year strategic analysis? And if you remember the forecasted 10 to 12% growth per year, we want to see how does the resource actually perform in terms of dock doors, associates, and the material handling equipment. Even at a smaller, a finer level of detail in terms of operational analysis, we can look at things like inbound door assignments for trailers, outbound door assignments for trailers. What new policies or approaches might we want to implement inside of our consolidation point, and how will they impact our freight? Because if we have a detailed model of a consolidation point, we want to make sure we use it to its fullest advantage. We don't want to be in the business of trying something new that we think might work in the real consolidation point, only to find out we made a terrible error. as you hopefully have learned at 855, if you have a valid simulation model, you can test those different policies, operational policies, in a simulation environment without impacting your current operations. And if you find something that seems fruitful in the simulation environment, then you might have some good ammunition to go up to management and describe why we should implement this process in reality. So what kinds of things are we going to measure here? Well, with a simulation model, we can actually look at things like utilization. How busy or how utilized are our resources? The dock doors, the people, the forklifts, the other material handling equipment. What kind of the floor space is being utilized? Do we have the right size consolidation point? In terms of the purchase orders, how many are we processing per week? What is their typical cycle time? Are we exceeding, or what percent of the time, are we exceeding our stated goal of a 48-hour turn? 48-hour turnaround time for when a purchase order comes in to our consolidation point, it is on an outbound truck within 48 hours. In a simulation environment where we're actually capturing the dynamics of the operations and the resources and the handling of goods and the cycle times and the queue times and everything else that comes into a dynamic model, we have the capability to measure these type of things. Also, we can look at our loading and unloading efficiency. We can see how long these purchase orders are waiting to be loaded or to be unloaded. What percent of our outbound trucks, for example, are leaving as less than truckload size shipments because we did not as fully load the truckloads outbound as we could have, thereby necessitating a larger full truckload shipment. As well as queuing times for the inbound trucks. How long are they waiting? All of these things are captured nicely in a discrete event simulation model. So the process that we used is we actually built a model. We did some animation to show the actual dock doors. You'll see here the different operations within the consolidation point. But we actually looked at these less than truckload trailers arriving, waiting for a free inbound door. Once a free inbound door is available, we would dispatch the truck to the door. Then now the truck's at the door. We have a certain number of purchase orders on that truck. We have details of every one of those purchase orders with regard to origin, destination, weight, and cube. We have different material handling equipments and methods of loading and unloading it, whether it's clamps, forklifts, slip sheets, carts. We go to very detailed levels here, as required by the retailer who sponsored this study, to look at different material handling opportunities and options. Each PO is unloaded from the truck. Either it's going to be cross-docked, as I mentioned, and sent directly to an outbound trailer that's ready to go to its intended destination, or it has to sit on the floor and wait until the appropriate outbound truck's available. And these outbound trucks, we have the ability to know what time they got on the door, what time they got on the dock, such that when 48 hours has elapsed, we know, okay, it's time to close the doors and ship this truck out. We actually can track this and start to dispatch and understand the operational policies within the consolidation point. So we have to be able to generate or simulate demand. Well, we have a 5-day operation. The retailer told us that any shipments that arrive inbound during the weekend are added to Monday's work. So we went ahead and modeled that. And we know that the retailer giving us information, we can look at historical data to kind of get an idea, some statistical and data analysis to characterize what a typical inbound shipment looks like. We get information about the number of trucks that arrive during each hour of the day to consolidation points. And this varies during the day, because the time of the day, as you might think, the number of trucks that show up at the gate at the consolidation point at 3 a.m. is potentially a little bit less than the number of trucks that show up in the middle of the day or near the end of the day. So we can compute the mean arrival rate of these inbound shipments as a function of time. So if you look at a plot of that, here's an example where we see very low arrivals early in the morning, and over the day, this picture shows it picking up over time. We can characterize this data with probability distributions and use this as an input to our simulation model, because we know the arrivals of inbound trucks to the consolidation point are not constant. They're not deterministic. The optimization model, a very high-level strategic model, was talking about the different routes that trucks can take and how many trucks we could expect. Here we're actually simulating individual trucks arriving at individual periods of time. So we needed to make sure we captured this arrival process effectively in order to make the input to our simulation model as accurate as possible. Once we have this truck coming in, we have to figure out where did it come from. Well, we can randomly determine the supplier's 3-digit zip code, because if you recall, we aggregated our suppliers by the 3-digit zip, to figure out by a discrete probability distribution where it's coming from. So if we have the probability that a less than truckload shipment came from a specific origin, we can do this just sort of based on a weighted average or a probability analysis that basically says if 4 of them came from zip code I and there were 100 of them total from all zip codes, then that means 4% of the time we could expect it to come from zip code I, and so forth. We make sure that because we divide each of the individual number of purchase orders divided by the total, as we sum up all of the possibilities for the 3-digit zip code, all of our probabilities will sum to 1. In other words, every shipment has to come from somewhere. So we could actually compute for ourselves, based on 3-digit zip codes, probability mass functions with regard to a specific consolidation point, and we actually did this for every consolidation point, looking at the highest frequency zip codes that send to this consolidation point. They get a higher probability value. And the simulation model is going to randomly sample and pick one of these values when it assigns the origin of a purchase order. However, we make sure that based on historical data, these first two, so zip code 648XX and zip code 727XX, have a higher probability of occurring because it seems that over time, looking at historical data, they typically get the lion's share of the shipments into this specific consolidation point. So when we look at the purchase orders, we have to figure out, okay, the shipment's coming in. I can tell you where each one comes from. I need to know how many are actually on a typical inbound truck. So again, looking at historical data, we make some assumptions. We assume that the number of purchase orders in a shipment does not depend on the origin or destination. We assume that it's independent of that. And we assume that it's normally distributed, but it's at least 1. So as we analyze historical data, if we ever find the mean number of shipments to be less than 1, we go ahead and say it's 1, because we're not going to say there's a partial shipment in our simulation model. More often than not, we're going to let it randomly sample from a probability distribution. So for consolidation point 6901, for example, we had a mean of 8.4 and a standard deviation of 5.1. Well, hopefully you realize you could sample from this. We could get all kinds of values. We could actually get values that are less than 0 if this is a normal distribution. We could get values that are in the 20s and the 30s. Well, we want to make sure that whatever value we sample in the simulation model, we never let it go less than 1. We make sure that at minimum, we're going to enforce with this max statement, one shipment here, one PO in the shipment, excuse me, but if this probability sample is larger than that, we're going to represent it as the larger value. So in this way, we're able to characterize the number of POs in each shipment. And as I mentioned on the previous slide, we know the origin destination of each PO. So this is starting to represent realistic data for shipments that are coming into our consolidation points. So I have also the purchase orders weighed in cube. Well, we have the idea that certain suppliers, maybe Pepsi, shipping heavy liquids like Gatorade, might be typically prone to have heavier shipments than higher cube. Whereas Procter & Gamble, Scott Towels, maybe they typically have a propensity for a higher cube shipment than weight. And so there's a lot of analysis that we looked at to try to characterize this. In the end, we decided to say that the weight and cube are supplier specific, so we could kind of tailor them based on historical data as to what suppliers typically ship to us. And we go back to the good old triangular distribution, because we have an idea looking at historical data of minimum, maximum, and most likely values. So here, bringing in an additional assumption, we look at Pareto's principle or Pareto's law, basically saying that 20% of our suppliers account for 80% of our purchase orders. And this is the case when we looked at historical data. So what we did was we actually said, okay, we're going to look at 20% of the suppliers and we're going to look at them in detail. But the remaining 80% of the suppliers that only make up 20%, we're going to kind of group them together. We're going to lump them together. So we're going to really focus on the 20% highest volume suppliers, if you will. When we do this, we can do some historical analysis looking at the different supplier zips, and we can get values of the minimum, the average, and the maximum for the poundage on a truck. We can look at the minimum, maximum, and most likely value of the cube on a truck. So we know by these high volume, the highest volume supplier zip codes. Now this is for one specific consolidation point. We obviously have to do this for every one of the consolidation points, looking at historical data. But we can sort of get an idea to feed into the simulation model of min, most likely, mode, meaning, or maximum. So the three parameters of the triangular distribution. Similarly, for the remaining 80%, we looked at the historical data, lumped them together, and we came up with, again, min, most likely, and maximum values for weight, as well as for cube. So now the simulation model, we have data that we need in terms of the demand process, the number of POs in a shipment, the origins, the destinations, the cube, the weight, okay? A variety of aspects that we have to characterize so that we can figure out on the inbound side and then the outbound side where they're typically headed to with the destination piece so that we can accurately simulate demand coming into our consolidation point. Coming in, knowing where it needs to get to. So those are kind of the brackets of the process, if you will. The front side on the inbound and then the outbound side. What's left is the internal workings of the consolidation point. The actual movement of stuff in the building. By whom, when, how far it travels, etc. So how do we look at the consolidation point's resources and processes? Well, we have to look at the purchase order level here. We know that a number of purchase orders come in on a shipment. We give them the different characteristics. The simulation model will assign the weight, the cube, the origin, the destination. Well, all of this directly leads to somebody needs to get it off of the truck to the proper location, whether the proper location is an occupied outbound door of a truck that's going to the same place that's ready for some cross dock, or if there's not a truck available, if it needs to be put on the floor and it needs to wait. This material handling equipment, whether it's forklifts, clamps, carts, slip sheets, etc., we actually modeled as individual transporters inside of the simulation model. Because there's not an infinite number of forklifts. There's not an infinite number of clamp trucks. And we need that resource contention in a simulation model such that things actually have to wait, because even though they're on an inbound door and there's an outbound truck ready for them, there's not a forklift available. This is reality. This is some of the power of a discrete event simulation model. And we know that these different types of transporters move at different speeds, and they have to travel different distances depending on where the inbound door is located at the consolidation point and where the outbound door is located. So with that in mind, we had to get some information from historical data. We looked at assumptions for the number of dock doors, associates, forklifts, clamps, carts, etc. The length of the consolidation point. The facility was 400 by 200. We have information on the percent of the time the loads are pallet type, slip sheet type, or floor loaded, because this is how it's characterizing them coming in on the truck. What type of forklift capacity, what kind of volume capacity do the different transporter types have? And finally, how many of these things do we have available? These are all pertinent inputs in the simulation model, knowing how the inner workings of the consolidation point are going to function. Because we need to know all of these dock doors and the length and the width and the capacities of these transporters and how many I have and the speed that they travel. And all of this leads us to how we model the loading and unloading process. So here we actually took some time studies. We went on site and actually looked at the operators doing their jobs and took 10 different samples at 10 different operators, tried to randomize our samples to try to get an estimate of the loading and unloading times. And by taking these 10 samples, we were able to average them together and get a good feel for typical unloading and loading times. We are able to get, based on the floor load, the triangular min, maximum, and most likely our mode value. We have for pallet, we have for slip sheets. So as you'd expect looking at the data, pallet loads are more quickly unloaded than floor loaded, because a pallet, a forklift simply has to go in, pick up the pallet, and move it. So it was nice that our time studies were confirming our intuition as to how long the process should take. In terms of the unloading process, we also were able to get floor, pallet, and slip sheet information. We also modeled that separately. Because unloading is different than loading, we took time studies on both. So if you're loading it and unloading it, that leads you to need to figure out travel distances. Well, when we look at the dock doors and the locations and the typical spacing between the dock doors and the size of the facility, we actually can do some rectilinear calculations to get distances from any dock door to any other dock door. With this type of calculation, it leads you to develop a from-to travel matrix. Well, why is this necessary? Because if you have resources in a simulation model that are moving within the facility at some speed, the next piece of the puzzle is how far do they have to move so that you can figure out the length of time it took them to move. So you look at the distance from bay 2 to bay 3 is only 36 feet, but the distance from bay 2 to bay 20 is 330 feet. So there's lots of travel distance here depending on the proximity of these different dock doors in the facility. We have the ability from 2 different dock doors to know the distance, to know the speed of the transporters by their type, how much they can hold, their loading, unloading time. All of these things go together to build the simulation study of things traveling within the facility, what I'll call the facility logistics piece. So far, if we've got shipments coming in, purchase orders with origins, destinations, quantities, cubes, volumes, and then we have all these interior pieces with regard to the transporters, the different material handling equipment, the people, the dock doors, the distances. We kind of have everything we need, all of the pieces in place to build our simulation model. Now, we have to figure out the final part is how we dispatch or decide the order or the operational rules of how things should be prioritized inside the consolidation point. So whenever a dock door becomes free, it could be assigned outbound, it could be assigned inbound. So we have to figure out, well, how does this assignment get done? Well, historically, it seems that there are 3 less than truckload shipments for every 1 truckload shipment. Said a different way, historically there were 3 inbound shipments for every 1 outbound shipment. So we probabilistically assign doors based on this 3-to-1 ratio. These inbound shipments are based on first comes, first served basis to an inbound door that's available. These outbound trailers are assigned to a door, again, based on the probability mass function we talked about before, based on whether or not the destination door has been assigned. And an active area of research here is this idea of the trailer to which dock it should go to, because you could have multiple options for where to put an inbound truck. Maybe there could be multiple doors open. Now, there may be some cases where you have a single dock door open, but in the event that there's multiple options, you making a decision is sort of the lead domino or can daisy chain into many other decisions you make later. If you have 3 different options and you decide to assign it to option A, later on option A is not going to become available for a while. And there could be something coming later in your process that it would have been much better based on the shipment characteristics and where it was headed, that you wanted it for A, not what you previously assigned. So this is what I'll call an active area of research. But we basically talk to the people on the floor who do this for a living and kind of build our own decision rules as to how they decide to make these assignments in practice. So if an outbound trailer arrives and if an inbound trailer arrives and an outbound destination truck is ready, we're going to do the cross-dock. We're going to offload the inbound and take it right over to the outbound truck. Now, this is assuming the outbound truck has capacity available, because just because it's ready, if it's already too full, we can't overload the truck, obviously. If we've put some purchase orders on the floor, on the bay, meaning they came off a truck that was inbound, but there was no room for them directly to go outbound, so we put them on the floor to kind of wait. If I have purchase orders that are sitting on the floor and the outbound truck is ready, I'm going to get them onto the outbound truck. So they're kind of our second level of priority. We're going to do the cross dock, but we're also going to be loading off of the floor into trucks if we can. If there's an outbound truck that's been sitting on that door for over 48 hours, which our sponsor, our retailer's desired turn time was, we make sure that, okay, is there anything else sitting on the floor? No? If yes, get it on the truck. If not, shut the door and ship it. We got to get it out. And if that outbound truck, as I mentioned, is at its capacity, whether it's at cube or it's at its volume limit, cube or pound limit, weight limit, we have to go ahead and dispatch it as well. So we built this model. We put all these pieces together. You have to figure out, does it work? So when we looked at the real system for a specific consolidation point, we got actual data for the expected number of purchase orders it would see over a desired period of time, the ratio of what they call the consolidation ratio, LTL to truckload, the maximum amount of time it spends, and the percent of late purchase orders. Late being those that exceed our 48-hour desired time frame. You'll notice our simulation model's quite accurate. It actually performed very well. I mean, here we're talking within a few percent of they expected 2057, and through our random process, they're generating the demand and the number of purchase orders in a shipment and how shipments come based on different times of the day, we generated 2029. Our consolidation ratio was close to 3-to-1. With the grace period they look at for a little bit of late based on the POs that are the purchase orders that are sitting on the floor that we have to quickly get onto the truck, I'd say that our 51.7 from the simulation model was very close. And similarly, the percent of purchase orders that we saw as late were also very comparable to their actual experience. So we felt really good about the fact that we collected all this data, made all of this analysis, built the model, and ran it. And through implementing their policies and probability distributions, we very accurately mimicked the real situation. Interestingly, our optimization model predicted an 84% dock door utilization at this consolidation point. The simulation model showed that it was about 83% utilized. So by looking at a strategic model, making some high-level calculations, we do the actual detailed simulation, and it matched up pretty well too. So we're feeling like we did some nice analysis here to take the strategic and look at the impact in the dynamic environment, if you will, the operational environment of a consolidation point. So when we look at some trends over our 5-year analysis, we looked at, okay, let's increase the demand in the simulation by the retailer's stated 10 to 12% per year. Well, as we increase demand, we see utilization of the dock doors and the floor space increase as demand increases. Well, that makes sense, right? If more demand comes, the doors are going to be higher and higher utilized. We also have the idea that as the demand increased, the time that a purchase order spends in the bay waiting to get on an outbound truck increases slightly, which makes sense as you have more things coming in. There's less places to put them on outbound trucks as the demand rate comes in. They're going to end up spending more time in storage on the floor. But we also see that as demand increased, the average time that an outbound trailer would wait goes down because there's more stuff to get on those trucks, gets them out the door quicker. These two are kind of complementary because even though we're getting them out the door quicker, it could be that some of the items in the purchase orders are spending extra time on the floor in the bay because there's no trucks available to put them on because we're getting them out quicker. So all of these analysis, what we'll call sensitivity analysis, really helped cement for the sponsor the fact that we had a valid tool for them to look at different operational policies, the impact of the demand increase. If they wanted to add some forklifts, how that would affect what was happening inside the consolidation point. This tool was very nicely developed to a nice what-if decision support system So they could look at a variety of different things and the impact of those potential decisions on the operations within the consolidation point, rather than going and buying a new fleet of forklifts and just hoping that it worked out for them. So what's your takeaway from this, the last lecture in this intermodal supply chain optimization module? Well, I would tell you that this iterative use of optimization and simulation, meaning, you do one, you can do the other. I could have used the simulation results to go back to the optimization model and kind of made this into a cyclical analysis here. It allows for some very insightful, smarter decisions to be made. And of course, this didn't come for free. I mean, doing these type of analyses is non-trivial. There's a non-trivial amount of time and resources that were required to perform this 5-year analysis for the retailer, the optimization piece, and the simulation piece. Truth be told, this project was a CELD Research Center project over a 12-month time horizon, funded at $75,000. This funds got 2 faculty members, myself being one of them, and I believe we had 2 or 3 different graduate students on this project. So it was a large-scale effort, not to mention the time that the company spent meeting with us, getting us data, sanity checking what we were doing. So this is not a free lunch here. I mean, this study was very powerful and very useful to them, but this type of analysis does not come for free. Now, my final parting shot at the consultants, and me being one, is that I don't believe there's any consultant who could have done this study any cheaper than we did. I think the academic bargain was priceless. Now, would a consultant be able to do it in less than 12 months? Probably. We typically do projects over a year time frame because it helps us work through them at the academic time schedule. We get students involved, and we make sure we do it right because unlike consultants, we're teaching classes and doing other research projects. But that doesn't mean we couldn't have done it quicker, but I think this scale of project required this type of time frame. And the fact that academic research can be quite impactful in your practice, I think, is something you all should be left with. The fact that we as faculty do have industry experience, we do have projects that we do for companies that can lead to tangible benefits and tangible return on their investment. So with that, I bid you good day and good luck on your next homework assignment.